class. Welcome to our second to last science seminar of the semester. Next week will be our last science seminar, and Greg Parker will be here to talk more about intellectual property and patent law specifically. So all you aspiring engineers and want to be inventors and patent yourself, you want to come on out for that. Okay. Today, though, we have Gitogo Churu, who's going to talk to us about some of his adventures at the Ames National Lab up there in Ames, Iowa. And I'm sure it's going to be an exciting thing for all of you to hear about things going on in Iowa. Iowa is a very pleasant place to be in the summer, isn't it?
Yes.
Yes, much far away from the heat of Texas, right? And
Not so good in the winter.
Well, it depends if you like snow. Yes. And so let's give a warm welcome for
So thank you so much for letting me do this. As you can see, this is my name. I am a professor here at mechanical engineering. But over the summers, I usually go to Ames. I think I have 2 more trips left because you can only go there 3 times. And I also work with a few people from other colleges, not just Ames. I have a chemistry professor that I work with, and I have a materials professor that I work with at Ames National Laboratory. And of course, we are also doing some work here. The aim is basically to bring this research here at LATU. So I'm collaborating with Dr. Demko. You know Dr. Demko, anyone?
You?
So we are working, and I have a bunch of, I think, 5 students that we are working with to basically try to bring this research here. So Ames National Laboratory is actually hosted by Iowa State University, and we actually have a student who is going to be working there this summer. So I'm excited about that. I will not be going this summer because I want to do some other things. It's also hosted by it's sponsored by the Department of Energy. So when I was working there, I was actually, my boss was Rick Perry, who is the governor of Texas, the former governor of Texas. So that was kind of exciting. So today we are going to talk about a material called aerogel. Has anyone of you ever heard of this material called aerogel? So we are going to see how we can actually, we have basically see what we have done in the past, the potential applications that we are looking for, and what we want to do in the future. So these are basically some of my collaborating professors. This is there is a group at UTD. There is some limit to what we can do here at LATU. So most of the time I go to work at UTD with a group there. There's also another group at MST. You know what MST means? Stand for? Anybody from Missouri? Missouri University of Science and Technology. And of course the group at Iowa State. And last summer, I took a student there. Her name is, you know her? Ever seen her? So me and her went there, and that is where we took these mug shots. And it's a relatively good place. And she actually did very well there. She did so well as some of the professors that we were working with were actually encouraging her to apply for a PhD, even though she is just, right now she is a junior. So this is actually very productive for students, and again, I'm happy to take a student each time I go there. This time, we also have a student going there. So she was working on catalysis, and this is part of the research that we were doing there. She made a very good poster. Obviously, she looks better than me, but that's beside the point. So most people don't know that this is during the Manhattan Project, the biggest part of the materials were actually processed at Ames Laboratory. So the uranium was actually processed there. So if you go there to work there are some spots that are still hot, meaning that you can go in and come out excited and illuminated, right? So there is also another place called the Critical Material Lab. This is where they make all kinds of exotic materials. I don't know whether you have heard about lead-free sodas. Lead-free soldering, that is now the big thing, replacing the lead in the soda. That material was actually developed there. It's a big cash cow for this place. One more thing that they have made is the glittering paint. Like you see cars and the paint is glittering. That one was actually invented or made there, and now they have a company. They are starting to form a startup to actually commercialize that. So they have done a very good job as far as material science is concerned. So briefly, I'm going to talk about aerogels, give you a brief history, and then I'm going to discuss how they are made, and some of the problems that we have faced, and some of the opportunities, typical uses, and then I'm going to focus on vanadium aerogel. Sorry I couldn't bring the materials here because I have this phobia that each time I bring the materials, I tell students not to squeeze them, not to apply any force, but that is the first thing that they do when they touch the material. So I don't want, if you want to see any one of these materials, you can always stop by my office. So aerogels are actually very lightweight materials that are extremely fragile. This is one type of aerogel that this gentleman is holding. It's actually from JPL, the Jet Propulsion Lab. And this is called silica aerogel. The silica aerogel that you see here can be made up to 99.8% air. We have made one that was like 99.2% porosity. This is the porosity. The other characteristic is that it can actually be 1,000 times less dense than glass, because glass is made of silica, right? So with aerogel, what we are doing is simply making them as porous as possible. We are removing as much of that density as possible. But the main characteristics, or the defining characteristic, is that they have a very high surface area, extremely high surface area. You can see something like 3,000 square meters per gram when you use this. So that is a big number, right? Also, they have a very high porosity, as you can see, like 99.8%. So these are the main defining characteristics. And because of that, they have these very unique properties. One of them is thermal conductivity. They don't conduct heat as well because of some of those porosities. Meaning, when you can actually apply a Bunsen burner, and the heat will not transfer to the next surface. We have a material that we are working, me and Dr. Demko are working with, and if you put that material in an oven at 150, you leave it there for 4 hours, you can actually take it out with your hands. 150 C, not F. That is close to 300 and what? 300 and something. So that is, those are really unique properties that we want to explore further. This, because of that porosity, they can also have some instability in them. So this is a material that I was working with when I was at Oklahoma State. And what happened here is that it's similar to this, but then I touched it with a Dremel tool, and it started burning extremely rapidly and filled the whole, almost the lab with smoke, and that was not the best night of my life. But you can see that they can have these instabilities in them that you can either take advantage of, or they can cause harm. So a brief history about aerogels is that they are not actually new materials. They were actually invented in 1930, around 1931, at Stanford by a guy called Kisler. And he was actually competing with one of his buddies that a gel, basically like a gel, is made up of a framework of solids. But the other guy was arguing that there cannot be solids inside the gel. Kisler was actually trying to prove that there is actually a solid framework within the gel. The key was to take out the liquid without damaging the framework, right? So in 1930s, he was able to do that, basically using a supercritical process, and I'm going to explain that in a few minutes. But then there was no use for them. For one, Kisler actually quit Stanford and went to work for Monsanto. Monsanto is a company that makes all kinds of chemicals, and that is where he decided that these aerogels, especially the silica aerogels, can actually be incorporated in toothpaste. So your toothpaste actually has some component, some remnant of this. And then, of course, they were forgotten. Nobody really cared for them anymore. Nobody cared about aerogels until 1960s and 70s, when the French government wanted to use, to be able to use liquid propellant. With liquid propellant on a rocket, there is this instability that can happen when the fluid throws back and forth, right? Well, it's just like you put liquid on a cup and then you can imagine what would happen. So the French government wanted to eliminate that problem by storing the liquid propellant in some kind of a solid media. So they decided that aerogels would be the best idea to put this propellant. And so from there they decided to use a different process, which is called the soil process. And we're going to talk a little bit about that in a minute. So this is your typical material. You can have different starting points. For example, all aerogels start from a metal alkoxide or something like metal oxide that is dissolved in a solution. And then you can either do a spin coating, you end up with a very dense film, or you can pass it through a spinning process and through a furnace, you end up with a very solid piece of ceramic. Another way is to go through this route, and this is the route that we are going to follow. It's called the soil process, where you force them to form some kind of a condensate, and then you can evaporate, and then you can heat. You can use the supercritical drying to maintain that framework. If you don't, if you just evaporate, you're going to end up with a solid piece, which is not something that you want. In this case, we have gone through that process, and when I was at UTD, we managed to use a ceramic piece plus an aerogel piece to actually stop a RF4 bullet. This is when I was working on a project sponsored by people who are interested in that kind of work. So we were able to stop it, but the problem was, if you look here, there is this, what we call the back face diffraction. Meaning, you stop the bullet, but then you have this big knot. So this is your body, and then you have a knot going into you. So that is called the back face diffraction, and our job was to reduce that back face diffraction in this case. So that was one work that we did. But for now, I will be talking about this process that goes to form aerogel. So most aerogels start like this. You have two precursors. You form a soil. You mix them and form a soil. which is basically a hydrolysis process. You want to wait a few minutes to age, and then after you age, you form those networks basically stay in place. They don't move anymore. And when that happens, if, for example, you use ambient pressure, it's going to shrink too much. But if you use supercritical fluid, then the shrinkage is not as significant as here. So our job is to maintain that, that network without breaking it. Because when we have this network, now we can add other components. We can add very interesting component to it that will either make it, customize it the way we want. This is how supercritical fluid works. I think you have seen this in your physics. Anybody have you ever seen this before?
In chemistry.
In chemistry, physics, almost the same thing, right? So when the fluid is under pressure and temperature, you can have this, this is called a triple point. You want to heat it and apply pressure to right around this point. And the reason that we want to do that is because we want to have this, what we call the supercritical fluid. And this is a fluid that basically behaves like a liquid and a gas. Meaning, as a gas, you know a gas is going to blow things very fast. So the transport of a gas is much faster. As a liquid, it can dissolve stuff really well. So when you have a fluid that has that good combination, you can usually use it to, in this case, you can use it to dissolve the solvent and then take the solvent out. We use CO2, and CO2 has a critical point of temperature of that around that 1 degrees and 73 or 74 bars. So whenever we are here, now we can use it. Why are we using supercritical fluid? Again, because we want to overcome what we call the surface tension. Remember, if you ever look at this is not going to work. Maybe we use this. If you have a fluid on a, it's going to form a, if you put a fluid on a regular glass, it's going to form this meniscus. So if this wall is not strong enough, it's going to pull this wall inward and break it. So with the aerogel, the walls are not strong enough, so they can easily break. And so if we use a regular fluid, then we can't be successful. So most of the time, with the supercritical fluid, it's going to form a surface like this. And when it starts evaporating, it's not going to cause, it's not going to pull this inward, right? So that is why we use supercritical fluid. But they are very expensive. The supercritical dryers that we see are usually very expensive. This is one from MST. This is one from another one from MST. This is from NASA. Just a 10-liter container cost of 1 million. And this is what we bought at UTD, where we did this work. So this one is not very expensive. So again, we have the process going, but we want to figure out whether we can do other things. Can we actually avoid supercritical dryers, which are very expensive, and try something else? One thing is we can use this freeze drying, where you basically freeze the sample, reduce the pressure, and then what? What happens to the fluid? It's going to subbrine. If you freeze and then lower the temperature, the pressure, you get a sublimation process going. Another thing that we developed while we were at UTD was to use a raw vapor fluid treatment. In this case, we try to mimic a supercritical fluid by using a fluid that doesn't have any meniscus. Meniscus is your enemy, so we don't want to use that. So that is something that we have done before. So now, why do we care about these materials? One is for thermal insulation. Dr. Demko and I are going to be exploring that. Acoustic insulation is also very good. Also, we can use it as a dielectric, something else that we'll be testing. And also for catalytic support, this is what we went to do at Ames, and I'm going to give a brief on that. And also as a host for chemicals, other chemicals. So we used some of the aerogels that we developed to host some other guests. We can also use it for filtration, optical sensors, aircraft structural components. We can also use it as a Cherenkov detectors. Do you know how this one works, by the way? Anybody knows how a Cherenkov works? No? So basically what happens is, if you have a radioactive or a nuclear power plant, you want to put something that can detect radiation particles. So what happens when those particles are released, if they go through the aerogels, they are going to be diffracted at different angles. And so just like when you put, you refract right. And so we can tell what kind of particles are being emitted from a radioactive source. And they can also be used for tissue engineering. This is something that we have done because it's so porous. We can introduce a cell, and that cell can grow. And for example, we can direct how a bone is going to grow. If we introduce a bone cell, we can actually do that. And that is work that is being done at Oklahoma State. I was involved briefly with it, but that is not something that I probably going to keep pursuing. Now, one of the most important things is that all these properties can be found within one sample. So you can have all these combination in just one sample. So they have actually been used, for example, to trap comet dust. NASA used this to trap a comet dust. Basically, they made this racket, and when the spacecraft passed through a comet belt, they were able to trap this within the material. Another thing that they have used for is to reduce the heat signature on an aircraft, especially the special unit, special forces helicopter, where they don't want to be detected. They can put a piece of aerogel, and that will basically reduce the heat signature in this case. One problem is that they are very delicate, they are very fragile, and as you can see here, these are some of the samples we tested. They basically fracture very quickly. Here, if you blink, you miss it. So, did you see that? So if you apply any kind of force, they basically, they are going to fracture. They also absorb water. This is a sample that we made again, and we just left it on the bench. And when we did that, this is all the water from the air that was absorbed by that sample. So you can see it can absorb quite a bit.
It's just like brushing tofu.
Yeah, you don't want to eat this one though. Good for you. Yeah. So also the supercritical dryer is very expensive. And if you look at this, when NASA wanted to make this racket, they had to actually make very small pieces and then put them together because they can't make one big piece. So that is something that we wanted to overcome. Basically eliminate this so that we can make bigger pieces. So aerogels can actually be made by most of these elements on the periodic table. If you look at the periodic table, you have all these beautiful looking elements. You can actually make aerogel out of them. The process is like, if you want to make an aerogel, you can either choose an organic piece or an inorganic piece. In this case, there is the natural ones, like cellulose. We can have man-made ones like polyurea, polyurethane. We have made all these. And also, if you want an inorganic piece, you can choose from all these exotic pieces. And each one of these is going to have special characteristics that you can use for special cases. So you can have either native aerogel, or you can also cross-link them, meaning you apply a coat of polymer, and then you can easily form what we call cross-link aerogels. So to make aerogels, you think of a 3D space like this. On one side, you can choose any of the nanoparticles that we saw on the periodic table, right? You can also choose a combination of them. Like the combination that is used in your car exhaust, especially the newer ones, is made up of this alloys here, or this one here. Or you can even have a tertiary component. The other thing that you can do is to change the morphology. So you can change the network morphology. In this case, you can come from something like this to something like this. This is actually the one we use to grow bone cells, because the bone cell has the same dimension, relative dimension to these pores. So if we introduce the bone cells, and if these aerogel pieces become the food for the aerogel or the media, then the bone cell will grow and multiply and then replace the aerogel with now a good bone. So if you have one of those hopelessly broken bones, we can always put this, but I will tell you to wait until we get clinicals done, so that you don't have other things that, otherwise the bad thing happen to you. We can also have this kind of morphology where you have, basically this is like a string kind of thing, or you can also have this type. So you can choose the nanoparticles, you can change the morphology. The third thing that you can do is to cross-link them. You can have all these and now use a thin layer of polymer to make them stronger. So if you start a silica aerogel, which are the basic aerogel that we have in our labs, you start with 2 vials, and then you mix them. You are going to gel and then age, form a soil and then age, and then you are going to do an exchange, some kind of a solvent exchange. Then you can dry it with a supercritical dryer to form a native aerogel. If on the other hand you want to add a polymer, you can add a polymer to basically make it stronger, and then you can at least end up with something like this. And that is what we have done here. We started with a silica aerogel like this, and then we cross-linked it to make it stronger. Basically, we are adding a layer of polymer, and without increasing the density. This was developed by a few years back. We developed it when we with this group at MST, and we have been working with them for quite some time. So this is the coating that we are talking about. And if you do that, we don't see any difference between the cross-linked and the non-cross-linked. They remain porous, but they are a little bit stronger. Polymers are something else we have done. We have done a lot of polymer samples. So again, we can change the morphology of those polymers and come up with all this good stuff. So one thing that we did is we are in mechanical engineering. We like to crush things. We like to make material suffer. So here we compressed it. And when we did that, it became transparent. Your physics should tell you what happened here. I can't remember. There is a process where something becomes transparent after application of pressure. This is another case where we have another aerogel, but this time we put copper oxide in it. So we have an oxide. The RF, which is this material here, was like a polymer. And then when we introduced fire, we completed the fire triangle, and this material can burn extremely fast and extremely scary, in an extremely scary way. So if you are ever burning this, make sure you burn it when you are, there's somebody watching so that they can come and rescue you. So that is basically how you make an explosive, but it's not good for you. The other material that we have worked on is called the vanadium aerogel. This is the material that we went to work with at Ames because we wanted to use it for catalysis. And again, the process is very similar to what we did with silica. And again, we did some compression test. And as you can see, when we did the compression test, we can actually compress it to a very high percentage. And then we tested it at minus 180. And when we do the test at 180 degrees, we got this really good curve, meaning that we can actually use this for installations when we have, when the temperature is really, really low. One instrument that uses this low temperature is your regular, what do you call it? The one that scans you when you go to the doctor? MRI. MRI and all those good stuff. So we can actually use it in this case. Another application that a group at Ames was studying is being able to incorporate some metal oxides or some other gas elements into the, and form what we call a nanocomposite. When you have a nanocomposite, you can actually replace this with, for example, a chemical that you can easily direct to go attack a tumor, for example. So how would you use such technology? If this, if you had a way of delivering chemicals to a tumor, this one can actually be used for therapeutics, and the guys at Iowa State are actually looking into that. So again, this is basically how the aerogel is formed. You have the saw, you force it to aggregate, and then you age it, and then you get to that point. So these are some of the records that we have seen: the lowest density, best optical index, lowest thermal conductivity, which we are going to be going through, dielectrics, and also all these can be found in the same component. So right now I'm going to talk about the organic aerogel, and similar to what we saw on when we saw the silica aerogel, you mix two files, and you can either form a gel or a precipitate, and then when you do supercritical drying, you end up with this. And these are some of the morphologies that we have done in the past. We also, of course, do a lot of this tensor test, which I hope we can do here. And in this case, these are some of the biggest samples that we have been able to do. And again, as mechanical engineers, we like to break stuff. And so this is going to break right there. So this is an example of that. And these are some of the data. We want to form, to get the tensor stress, tensor strain, so that we know how much this material can take before it breaks. And this is actually very good data, right? So another thing that we do, we have done it, especially at UTD, is to use high strain dynamic test setup like this. We put the material here and put an impact, and basically the material goes here, and then we use a high-speed camera to observe. In this case, we had a camera that could record up to 3 million frames per second, but here we needed 60 frames, 60 60,000 frames per second, and so that we can record that event. And this is where we recorded that. And this is the result of that impact. So this is at maybe, I don't know how many frames per second were those, but this is how the impact happened. And of course, we can generate the data that we want, the mechanical property data, whether it's modulus, yield strength, and all the other good stuff. We also did quasi-static tests, and in this case, again, we are just going to compress the samples, and in this case, we put it in water because we wanted to see how does the mechanical property change when the sample is soaked in water.
So it doesn't shatter like the one that you showed us at the beginning.
This one, this is organic, so it doesn't shatter as much as this. It took a few iterations to make it not do that.
So are organic ones less fragile than inorganic?
They are less
ones?
fragile, but still fragile. Yeah, you had to. This was at the first strict control so that you don't get the fracturing to happen as much as we wanted. So this is the data that we get. We get compressive and tensor strain, and all this we did that for a lot of samples, and we got this series of data. So we also did another test. This is where we decide to do repeated loading, and we did that, and as you can see, we are able to get this hysteresis graph in this case, and also something like this. So this is where we repeatedly abuse the material to see how much it can take. And by the way, this is something that we can do here. We have an instrument that can do this, so that is going to be a big help. And so this is the data that we got. This is I would like to for you to pay attention to this, the specific energy density of this material. It's relatively high compared to other materials. We always like to compare any material you develop. You want to compare it with what is found in nature. What is the strongest material in nature?
Spiderweb.
Diamonds.
Diamond, spiderweb. So the spiderweb has a specific energy density of 169 joules per gram. That is like it's much better than Kefra and all the other materials. That's why you see in the tropics there are spiders that actually hunt birds, right? Because the bird will just smack the spiderweb and get trapped. So if we can get as close to that as possible, then we are in good shape. And also, our advantage is that we can do it at lower temperature and still maintain really good energy absorption capabilities in this case. So these are some of the tests that we have done. But another thing that I want to talk about now is on acoustic tests that we have also done in the past. So this is an acoustic tube that is in RPI in New York. We use it to basically test the acoustic property. So in this case, we put a sample here, and we listen. We set an incident wave, and now we can listen to that material and see whether there is anything that this mic is going to read. So this is how normally the sound wave is. We anticipate is going to happen when the wave is traveling through porous materials. It's going to be broken up continuously as it travels, and when that happens, it's absorbed. The energy of the wave is absorbed. So this is actually very important because of what is happening, has been happening in the last few years, where we have the cases of burst waves. So if you look at a wave, a burst wave, let's say this is a burst wave, it's smacking your brain, it's going to cause this kind of event to happen in your brain. this basically is trying to pull the brain apart and then bring it up, basically strain and stress. So this is a big problem, right? So what happens when a blast wave happens, especially whenever there is an explosion, the wave actually starts traveling through your brain like this. What makes this even worse is sometimes that people are wearing helmets. You think that is a good thing, but what happens when you're wearing a helmet, especially a hard helmet, is that the wave does not get out of the head of your head. So instead, it starts pinging back and forth, and when it's doing that, it actually gets amplified. So it actually worse for somebody wearing a helmet, especially if it doesn't have the proper insert. It's actually worse than if you didn't wear any helmet, because the wave will just go through and go on. So when that happens, if this is your brain before the blast wave, this is your brain after. So this is the, what do you call this? This is the, how your neurons are going to look like after this. So this is a big, big problem. We need to be able to basically block or at least absorb that energy. So with our material, with the material that the military has been using, this is similar to this. Basically, this is the acoustic wave that they have been using as far as the inserts are concerned. But with aerogels, you can see that they can absorb a lot more energy than what you see here in this case. So if we could replace the pads that are used by the military with pads that can absorb more, we can actually save lives. We can actually change the game quite significantly. So they actually gave us, we were working with the DOD, they gave us some helmets, and then we took out the inserts and replaced these inserts with aerogel helmets. And then we built this tower at UTD, and we were able to do some impact test or drop test, and then we would correct the acceleration data that the insert sees when it's in service. So these are two, let me see, to pray. So these are the two pads. Now I want you to look at the impact on this guy. Now you see that thing going away. It's not going to come back anytime soon. Oh, it's going to come back. There it is. And then it's going to bounce back a little bit. But look at what happens when you do an aerogel drop. So what does that tell you? So do you want your head here or your head here?
My head anywhere.
So, but if you don't have any choice, where do you want your head? So this one, you can see basically by simple logic, you can see that this guy did not absorb any energy. That's why the thing is bouncing up and down and going through the roof. This guy just bounced a little bit, and then everything was attenuated. So that is why we wanted to replace this. Now, if you look at the aerogels that we were using, this is the SEM. It's basically made up of small squishables that are like 5 micron across, 5 micron diameter. And when you have this arranged in such a way such that the impact is not transferred throughout the material, then you can have very good results, like the one you saw a moment ago. This is a piece that we actually made, and we tested it. The problem here is that this density is way too high. So in the last few months, we have been working to reduce this by 10 times. So we wanted to be, instead of 0.52, we wanted to be 0.05. So that's what we want to do with that. Now, this is the data that we get when we do the impact test. This is basically the acceleration that we get. We can go as low as 100 G. The military department of, it's called DOT, Directorate Operation and Testing. Their top number was 150. They wanted us to stay below 150 G. But right now, the newer generation that we have come up with is going up to right around 60 something. So we are headed in the right direction, but still work need to be done, especially to reduce the density so that it can actually be applied. So what we have done so far is come up with a newer type of aerogel that can actually absorb more energy, and we can actually make it in bigger sizes. Remember, NASA cannot make bigger sizes because they haven't innovated enough to where they can replace the supercritical dryer. Us, we can replace that, and we are kind of happy with that. We basically did that by replacing the supercritical fluid with a low vapor solvent treatment that actually I can explain further if you need to. And we can actually make them bigger. We can make much bigger samples. The other part of this is what I was actually doing at the same time when I was at Iowa, is being able to convert biomass into biodiesel, biofuels, and all the other things. You know that the Earth's surface is made up, we have a lot of this grass, and especially in Iowa where they grow a lot of corn, they would like to basically turn all those, whatever is left of after they harvest the corn, they want to be able to use it for something other than throw it away, right? So in this case, our job was to develop a catalyst that can actually help degrade this biomass into biofuel or biocomponent. The problem is this material is made up of something called cellulose and also something called lignin. Lignin is one of the components. And if you look at the structure of lignin, it's extremely complex. Our job is to try to break up those bonds into something smaller, something easier. And we found out that we can actually use, for example, we want to break it up into smaller molecules. From this complex molecule that you saw here, we want to break it up into fragments. And then hopefully we can basically select them and then filter them and use them any way we want. So other people have done it, but they have used vanadium to catalyze this. But what we wanted to do is, because aerogel has such a high surface area, we wanted to see whether we can introduce other guest chemicals. The one that we were targeting is the platinum group. Ever heard of the platinum group? It's not a musical bird. It's part of the periodic table that has all these platinum-based. They call them platinum group. I'm not in chemistry. I'm in materials in other department, but there is a section in the periodic table that is called the platinum group. So we wanted to be able to introduce those groups because they are very good catalysts, so that we can cleave this board and form something like this. So another thing that people are looking at is methane is a very simple molecule. What if you add, methane is CH4, right? Methane is CH4, right? What if you could make it C2 or C3 and then something else? Then you could have you could actually convert methane into something more. That is a very hard process to do. So you need a really good catalyst to be able to convert the CH4 into C2 and something else. Basically increase the number of carbon atoms in that molecule. So it's a terribly hard, complex problem. But you can use a catalyst to do that. And that is what we are trying to see, because we have a lot of natural gas, and we probably can do something else with it. So that is what how we started on this, because I can see Dr. Boss is looking at his watch. I'm going to go faster here so that we have time for questions. So we look at the lignin literature. Again, we go back to our roots, which is making catalyst, and then we build this catalyst using the same process, but now we included palladium into the mix. When we put palladium, this became a very effective catalyst, and this is what Ms. Brooke was doing over the summer. So this is where we are right now. This process is going on. We could also add activated carbon, and then we ended up with another catalyst. So this is what we are trying to do, to use this to cleave those lignin boards so that we can produce something else other than what you have seen in that complex molecule. So there is still some work to do. We need more research. We are also looking at gas phase reactions that can be catalyzed by this kind of a catalyst. So gas phase reactions are terribly hard to do. So hopefully we can do from CH4, we can do something like this and produce something most manageable or better than that. Hopefully that was not too quick.
Because of the hour, if you have questions, you can come down and ask Dr. Churu. I also want to just let you know that Pine Tree High School is here today. So why don't you Pine Tree students stand up here so we can greet you. Let's all show some love for the Pine Tree students. And next week we'll see if any of this work by Dr. Churu is patentable when we talk to our patent attorney. So see you all next week.
Okay.